basics of deflection and the causes of deflection. We will also look at some factors that affect bending. Next, we will examine two examples of deflection on a cantilever beam and a supported beam. Deflection is the measure of the deformation in a structure and its structural members. Most structures are designed with stresses as the primary design consideration, but deflection of the structure is also important. In fact, deflection is as important a consideration as the strength of the building's materials, especially when designing long support spans such as beams. Stiffness is, therefore, an important component of deflection. Deflection is referred to as either a change or movement of a structure in a vertical direction when placed under a load, or as a scalar value that describes the distance that a material bends when placed under a load. Formulas are used to calculate the deflection of common structural elements. Beam-like structures are a part of products that humans use every day. These include, but are not limited to, diving boards and other cantilever-type structures, roof supports and trusses, axles, bones and medical equipment, wings of airplanes and bridges. Before such structures are built, bending analysis calculations must be performed. Deflection is caused by more than just the live and dead loads it supports. How much a structure will deflect also depends on the geometry of the structure, the material that is used to build the structure, and the physical properties such as environmental extremes and structure support. The load is the amount of weight that the structure must carry. Weight might be the snow on a rooftop or the individual standing at the end of a springboard. The load is represented by a vector and possesses units of force, either force per length or force per area. There are two general types of loading that affect the bending of a beam: a point load and a distributed load. The point load is a mass that can be represented by a single vector at one spot along a beam. A good example is a person on a balance beam, where the point load is established at the person's center of mass. A distributed load can be any shape. A distributed load is comprised of a weight occurring over a span of a beam. The weight can be equally distributed, or it can be unevenly distributed, as the case of a pile of rocks in the bed of a truck. When we talk about bending, three factors must be considered. They are the material property used to build the structure, the physical property or the geometry of the structure, and the beam or structure supports. The geometry of a support structure is the two-dimensional image of the structure or beam. These are two different support structures made from the same material. One is cut to a different size. The supporting loads, which are on different sides, will deflect differently under the same load. The method in which a beam is supported is a definite factor in how much a beam will deflect. For example, compare a person standing in the middle of a diving board and a person standing in the middle of a bridge made of the same material. We will assume that the springboard and the bridge both have the same geometry and therefore the same moment of inertia. Moment of inertia is the rotational analog or measurement of mass. Since both are made from the same material, they have the same modulus of elasticity. Modulus of elasticity is the mathematical description of an object or a substance tendency to be deformed elastically when a force is applied. The resulting deflections will be much different because of the nature of the beam supports. In reality, the resultant bending would be as illustrated. Supports are important because deflection equations are generated from four integrals from the loading points. Yes, for you calculus fans, that is, integrating an equation 4 times in order to derive the deflection equation. The supports are used as boundary conditions to solve for some of the constants of integration. Now, let's calculate the maximum deflection on a spring diving board. We know that the diving board is 12 inches by 2 inches and 72 inches long. Also, the diving board is made out of pine, which has a modulus of elasticity of 1.76 times 10 to the 6 psi. The person jumping off the diving board weighs 250 pounds, which is the applied load on the diving board. To calculate the maximum deflection on the cantilever beam diving board, we will multiply the applied load times the cube of the length of the board. Then we will take the answer we just found divided by 3 times the modulus of elasticity times the cross-sectional moment of inertia. Formally, the moment of inertia is defined as a mathematics property of the cross-section of a shape. It quantifies the stiffness of the beam due to its geometry, and is calculated about the center of mass, or the centroid. The higher the inertia, the more resistance a shape is from bending. Let's solve our problem. We will begin by identifying the moment of inertia. To calculate the moment of inertia, take the area of the cross-section, or base times height, and multiply it by the height squared, and divide by 12. The constant 12 comes from the deviation of the equation using a calculus. In our problem, the first step is to find the cube of 2 inches. Next, we take 12 inches times 8 inches cubed. Finally, we take 96 inches to the 4th divided by 12. The moment of inertia is 8 inches to the 4th. Now that we know our moment of inertia, we can plug all the information into our maximum deflection formula. We must find the maximum deflection of a 12-inch by 2-inch pine diving board that is 6 feet long and carries a load of 250 pounds per foot. First, list the formula. Plug in all known information. Determine the cube of 72 inches. Now multiply the top numbers together. Then take 3 times E, which is the elastic modulus. Now take the inertia of 8 times the psi number and simplify units. Divide the top number by the bottom number to find the maximum deflection of the beam, which is 2.21 inches. Now let's calculate the maximum deflection on a pine beam in a structure. We know that the beam is supported by a pin at one end and a roller at the other end. The beam is 4 inches by 6 inches and is 96 inches long. Also, the beam board is made out of pine, which has a modulus of elasticity of 1.76 times 10 to the 6 psi. The 200-pound applied load is placed at the center of the beam. To calculate the maximum deflection on a cantilever beam supported by a pin at one end and a roller at the other end, we will multiply the applied load times the cube of the length of the board. Next, we will divide by 48 times the modulus of elasticity times the cross-section moment of inertia. To solve our problem, we must first calculate the moment of inertia. Take the area of the cross-section, which is base times height, multiply it by height squared, and divide by 12. The constant 12 comes from the deviation of the equation using calculus. In our problem, the first step is to find the cube of 6 inches. Take 4 inches times 216 inches cubed. Finally, divide 864 inches to the 4th by 12. The moment of inertia is 72 inches to the 4th. Now that we know our moment of inertia, we can plug all the information into our maximum deflection formula. We must find the maximum deflection of a 4-inch by 6-inch pine beam that is 96 inches long and carries a load of 200 pounds per foot in the center of the beam. First, list the formula. Plug in all known information. Determine the cube of 96 inches. Now multiply the top numbers together. Take 48 times E, which is elastic modulus. Now take the inertia of 72, multiply by the psi number, and simplify units. Divide the top number by the bottom number to find the maximum deflection of the beam, which is 0.029 inches. This information will help you get started with beam calculations. Depending upon the object being supported and the application of the load, different variations to the maximum deflection formula may be used. With some more practice, you will be able to successfully